about where we were yesterday and where we're going to go today, because I just gave you guys some cards, and I want to play with cards today to extend what we were doing yesterday. Here's a synopsis of what we did. I got our computer back. So the first problem that we did in class was I gave you a coin, and I said flip it until you get a repeat. So flip it until you get either two heads or two tails. And we figured out pretty quickly it takes a maximum of 3 flips. Because if you go heads, tails, or tails, heads, the next flip is going to match one of the ones you already had. And if you go heads, heads, or tails, tails, you're done. So it's either 2 or 3 flips. And then we thought about, okay, on average, how long should it take to get a repeat? And we didn't use our data to figure that out. We just said, on average, how long will it take? And our conclusion was, how long should it take? Do you remember? On average, how many times should it take to flip? The answer doesn't make a whole lot of practical sense. 2.5! 2.5! And you're like, wait a minute, you can't flip 2.5 times. You're right, I can't flip 2.5 times. But all that says is, for each time it took me 3, there was another time that took me 2. That's 5 over 2 flips, which is 2.5 over 1 flip. It's just dividing down so it has a denominator of 1. Does that make sense? It's like an average grade. Right? Iowa Street, you guys analyzed, this is going back about 3 weeks now, but you guys analyzed Iowa Street, and it had an average rate of like 5%. But there was a section of Iowa Street where the grade was extraordinarily steep, and there was one section, which I didn't have you calculate, where it's actually going downhill a little bit, not uphill. So it averages out to 5%, even though very little of the road is actually at 5%. Same thing here. The average is 2.5 flips. Even though you can't actually get 2.5 flips, it averages. Remember what the definition of an average is? What word comes to mind? Brittany nailed it for us, I think, about a week and a half ago. When you think about an average of anything, whether it's coin flips or grade or whatever, what is an average? The middle. I like that, Pam. I like that. It's the middle. How do you mean middle? How does Pam mean middle? Or how do you guys mean middle? I love that word, by the way. That's center. Center. I mean the middle. I mean what I mean. I mean what I said.
No, I was going to say the lowest and the highest, let's say, of a number, and then figuring out approximation of...
That's center.
Yeah.
Good, center, yeah. Good. Somebody put, I forget, I think it was Brittany. I'm almost sure. Maybe it could have been Ashley. Maybe. The medium? If you smoothed out all the fluctuations of the data, they'd all be the average. So here's what I mean by that. What's the average height of a person in this room? Make up a number, because I'm not going to calculate it. Could we call it 5'6", make the math easier? It's okay. 5'6", okay? I'm almost 6 feet tall. That means I'm 6 inches above average. If the average is 5'6", that means I have to take my extra 6 inches and donate those inches to people that are below 5'6", in order to get them up to 5'6".
Like when we did the water thing.
Yeah.
That's it. It's the same as that, Christina. So basically, what an average is I mean, it's a strange term. It's a socialistic measure. It takes every data point and makes them all the same, but it makes sure that you still represent the total number of things that actually happen. So for every 6-foot person, there's a 5-foot person that share the extra or needed 6 inches to balance out to 5'6". Exactly. Perfect explanation on the end of that. Exactly. So that's what an average is. So that's what it means. It would take us 2.5 flips if every single time we had the exact same result. Now remember, you can't get 2.5 flips, right? You can't get 2.5. So that means for every 3 there was a 2. And for every 2 there was a 3. And our data looks kind of like that. Now we had slightly more 2s than 3s. When we actually crunched our numbers, we had 96 2s and 86 3s. But then we calculated the average. Remember how we did it? Remember what kind of average it was? It starts with a W.
Weighted.
It was a weighted average. The most important kind of average, in my opinion. The most important kind. So there were 96 2s. So one way to do it is to go 2 plus 2 plus 2 plus 2 plus 2 plus 2 96 times. But we discovered that we could just do 96 times 2 to get 192. And then we could do 86 times 3 to get 258, which means we had 450 total flips that we all did. And what the average does is it takes those 450 total flips and divides them up into equal piles. So you divide that 450 by the 182 experiments that we did, and you end up getting an average of 2.47, which is damn close to 2.5. Damn close to 2.5, which is what we thought it should have been anyway. Now, can you explain this discrepancy? Explain it in a couple words or a couple phrases. What's the discrepancy? How come we got more 2s than 3s?
Chance.
Oh! I heard two wonderful words. I heard chance,
Chance,
and I heard error. Good, and this is a good error. It's a good error. I would be very surprised, actually, if that came out to exactly 91 and 91, which is what it should have been if you split 182 halfway. I'd be very surprised if it came out perfect. So chance, error, explains all of it, actually. Amy, yeah.
Randomness?
Random and chance, I call them potato. But yeah, randomness. I mean, there are some times where this will go higher. I mean, it's just one of those things. It's chance, it's random, and error happens. You're always going to have messiness to deal with. That's why in 243 and 244, we start slapping margins of error on things. We mentioned it earlier in this class, and I like mentioning it in 105 in case you guys aren't taking up later stat classes. But still, there are measures for that. We figure out how to do them as we go. Cool? All right. Now, we did that one in class. What we didn't do in class was this one. Here is the graph of, let's go over here. We'll hide the average for now so we can calculate it. Here's what we did second. The second experiment was keep flipping until you make sure you've seen every side. This was different than flipping till a repeat. Because, for example, flipping till a repeat, if you went tails, tails, you were done. Here you weren't. You had to keep flipping until you saw heads. And unfortunately for some of us, that took a lot of flips to actually get there. We had a 12 and a 10, kind of fun. So here's the results. 90 of us needed 2 flips, which means you went heads, tails, or tails, heads, and we call it a day. 35 of us needed 3, which would have been tails, tails, heads, or heads, heads, tails. Right? 30 needed 4, which would have been tails, 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 heads, or heads, 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 tails. Right? Making sense? And then so forth and so on. And you see, if you look at the graph of the results, what does it kind of look like? What kind of graph does that look like? I know it's messy because it's real data. What does it look like?
It's kind of an exponential regression.
And it should, thank you, Josh. And it should look exponential because it gets twice as hard to keep flipping the same thing versus alternating over. But think about the runs. Tails, heads. Tails, tails, heads. Tails, 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 heads. Tails, 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 heads. Those, as I'm talking and getting those strings longer, it should be harder to get those later strings, shouldn't it? Remember my stat professor who famously misspoke. I saw tails 12 times in a row. You don't want to bet on heads next. Why? I mean, this person right here was thinking the same thing. Oh, God. Oh, God. I just saw 7 heads, or I just saw 9, or There's no guarantee you're going to flip over the next one. That doesn't mean it's not hard to get a string. It is hard to get a string. But looking to the next flip, it's still 50-50. So hopefully that makes sense, and it should look somewhat exponential. Half as likely each time. Good. So on average, how many flips would it take? On average, how many flips? What do you think?
4.2.
4.2?
Just a guess.
Good. I have it up there on the screen. I had to calculate. I hit it real quick. I should have hit it earlier. Because I want us to calculate it. I want us to make sure I want to use technology to calculate these things. I do, I swear. But I want to make sure you know what calculation is happening before we actually do the shortcut with technology. Well, can we apply the same logic we did before? Christina's nodding vigorously. Yes, of course. It's a weighted average, right? But let's get some guesses first. I guess for 4.2. Other guesses. With the average, it would be an average of these values or something between those values.
Between 3 and 4.
Between 3 and 4. Good answer. I like the between 4.2, between 4 and 5, between 3 and 4. Anybody say pi? Very nice. Touche. Anybody say between 2 and 3? 2 and 3? Between 3 and 4?
Yeah.
Between 4 and 5? Good, good. Let's come back to that. You can approximate an error with a graph pretty efficiently, but let's come back to that. Because let's do the calculation, because we've been talking about that. This is going to be a little bit tedious, a smidge tedious, because you have so many values, but let's take our time and work our way through it. We'll go over to the sideboard here. And then we're going to learn technological shortcuts, because this gets annoying pretty quickly. Yeah.